now, and like this. Okay, perfect. Okay, now we are recording, and we see the same screen. Nice. Hi. First of all, thanks for coming. I mean, sorry for that changes in the schedule. So I don't think that, I hope it won't happen until the end of the course. Some comments on lab 3, and it was one message in Discord that I somehow delayed with the response about the MAD file. And then it was a question before I started regarding lab 3 and pre-processing. So there are different opinions how to pre-process text. So whether so here I can only say that there is no ultimate solution or ultimate answer to how to pre-process text. You can do different stuff. So you can do lemmatization, you can remove stop words, you can do other stuff, or you can probably resort to removing special characters, punctuation, and such. The performance could be different, but it's again, so machine learning and AI is not exact. Well, the discipline is exact, but the results are stochastic. So the only way you can tell which method is better is to compare the performance. And then, so there was a question about this math file. So well, it's a file generated in MATLAB, but it's not MATLAB code. It's a data set. It's a data set of languages. So it's very it's already pre-processed text. So you can import it to Jupyter and check the way how the text was pre-processed. But I made it as a task in lab 3 on purpose to try for you to try really work with the raw data. So you download the news, and then you see that, I mean, it takes lots of time to actually pre-process this text in an automated way, because but then maybe practical hint, but again, so that's maybe, I mean, you understand yourself. With the when you work with data and algorithms, so it's very natural to try your method, your model on smaller data sets, just to so maybe you can download 1, 2, 3. Well, one or two is maybe very simple, but case, but say 3, 4 data sets to try out. Make smaller versions of this data set just to try your pre-processing routines. When you are happy with the outcome, then you should expand your script for processing of larger data sets, because as you understand, again, so practically it takes lots of time. I mean, every run can take lots of time, depending on the size of the data and the complexity of the algorithm. So try with something small, and when you're happy with some kind of first stable results, so make an automated script to scale your script. Again, when I say script, that is another kind of advice. I mean, of course, and I know, so even some researchers, at least in the beginning, so I mean, the tendency is to try some things manually. So, for example, you train you write your code where you kind of hard code the data set and basically make a single run for training. And then especially when I say, okay, so try with different seeds, because I mean that is the way to produce statistics. well, again, so you sit and think, okay, I try 3 or 5 different seeds, and I can do it manually. And then, but again, the larger is your problem, the more complex is to keep track of what you're doing. So, and as such, so make a rule for yourself from the beginning to automate your actions. So create some scripts. So, I mean, some generic scripts where you process data sets, you you have several iterations. On each iteration, you choose, you change seeds, try different parameters, whatever you do, and then automate the recording of the statistics. That will, at the end, it really worth it. I mean, you will see it, because otherwise it will be really logistical nightmares to work with it. Yeah. Any specific questions? Or maybe, yeah. I will talk about again this lab 3 in the context of this class, but as I said, so this class I inserted several years ago, so on purpose. So it directly connects to my research here, well, that I do at LTU, and it can be useful in many, in several ways. So first, technically, so you can use the techniques that I present in your learning pipelines, and so I will try to show the place of this technique, which is called hyperdimensional computing, in the scope of artificial intelligence or artificial general intelligence. But also, I think I can use this moment and tell about my kind of ongoing collaboration with a group at La Trobe University. So there is a group called Center for Data Analytics and Cognition there in Melbourne, with whom I really I have really tight collaboration. So they are on adjunct positions here. So the profs, and I'm an adjunct professor there as well. But what can be practically useful or interesting to some of you, at least, is that this year it is the last year we run a mobility program sponsored by STIMT. You know, I don't know if you haven't heard about it. It's Swedish Foundation for Internationalization and Higher Education and Research. So and so basically it's a project that we run together, and so as I said, so this is the third year of the project, and as part of the project, so I can, for example, support master students, or students doing thesis work, going for maybe 2 or 3 months to Melbourne, and we can define a topic. So, and there you will work with my PhD students, whom I co-supervise with this, with the profs over there. So, and the core of our collaboration is basically the topic that I will talk about today, but also unsupervised learning. So unsupervised learning somehow is particularly interesting to me. So, and because of different reasons, I think just the primary motivation is pure curiosity, because in biological systems we have lots of unsupervised learning. So I mean, we can train in an unsupervised / reinforcement manner a lot. So the supervised part is important, of course, and but it's kind of cherry on top of the cake, so to say, with respect to learning and cognitive abilities. And so already next class, I will be talking about self-organizing maps, and this is a neural architecture for unsupervised learning. And actually, the group over there, so they were very active in unsupervised learning using self-organizing maps historically. So I mean, and basically, so unsupervised learning slash this topic I will be talking about, plus in general data science or data analytics. So that would be the large areas where we can define master thesis. And I think I can tell you, it was very unfortunate that we started this project during COVID time. And I had 2 students who wanted to go there. Only one managed because of all these restrictions and such. But it was a successful stay. So okay, if you want to know more, so you know how to reach me. Maybe the last curious fact is that this La Trobe University has same acronym, the same short name as we do. So it's LTU. So that's why we call our collaboration like LTU squared. And Melbourne is a fantastic city. I didn't tell it. Yeah, of course, it's much nicer to be here in snow and darkness. Yes. Again, so I created this presentation for actually really as an introductory talk. Targeted to diverse audience, starting from really public with little knowledge about machine learning or AI, but also people who work with AI and knows at least fundamentals, and look for kind of methods to broaden their toolkit of methods that they use, but also those who look a little bit ahead towards kind of specialized hardware for really implementing functionality, artificial intelligence functionality, and as large questions of artificial general intelligence, which despite what OpenAI people claim. So did you read this news? They asked Microsoft for some billion again, and they promised to create AGI like very soon. I still think I mean there is quite some degrees of freedom to do different versions of it, so to say. But nevertheless, so we will be talking about different concepts here. So we will be talking about artificial neural networks, but also linking to biological neural networks and hardware based on these principles, like neuromorphic stuff. I guess some of you, at least from the program students, probably you read you took this course of Fredrik Sandin. I don't know. Did you take his course? Yeah, about learning machines, something. So where the focus is on neuromorphic hardware. Here, I'm only touching this area. I mean, in my research, I really cannot position myself as a researcher in neuromorphic artificial intelligence, but I can. So in few slides, I want to deliver one. My standpoint on this, and we will be talking about artificial neural networks and computers. So basically, the hardware that we have for different kind of computations. I already published some links on Discord where you can get some extra information, and moreover, so if you want to know kind of more technical details on this area, so there is a course like in several proper lectures which was given by or was created by my former PhD student who did postdoc at Berkeley. And so it's a really good course. So you should probably, I would definitely advise you to read it. Then we have a really cool publication, and so that's a very prestigious magazine. So it's technical, but it's a magazine. So it's not a scientific journal, but it's a magazine kind of delivering kind of the cutting edge results already, which are underwent the review process in good quality journals. So here in this publication, so we are talking about this theory and computational framework really as a paradigm for next generation hardware. Yes, then there are, again, this resources, electronic resources. So this is gcomputing.com. So it's a website that gathers all the information. So it's really the latest cut, the state of the art there. Then this is my webinar. So I kind of lead it every second week since 2020. So at 10 p.m. just to cover, you know, people both in the States and in Melbourne somehow. So every Monday. So and I have collected quite some videos on very interesting topics, amongst others, kind of relationship of this theory to transformer networks. So how it can, how this theory can help in, for example, boosting performance in transformer networks and other stuff. So you can have a look over there. So I will not go through it. And then we have also a mailing list for the community, in the case you will be interested. Plus, so there are libraries if you want to try again. So those of you curious and skilled in programming, so you can. So these primitives that I will be talking about, so they all implement the library, so easy to use. Yeah, and I have structured this class in two parts. Basically, in the first part, I want really to I want to talk about computers, this neuromorphic electronics, the idea behind it, types of it, and challenges associated with this hardware. And in the second half of the talk, I will talk more about this computational technique in the scope of AI machine learning. So again, so probably I will repeat myself. I definitely said it many times, but and you probably know it even without me. But the main bottleneck for AI functionality is computing, really. So the computers that we have, so this von Neumann built using von Neumann architecture, so with a CPU and a memory and a bus in between, and you know, shuffling the data back and forth, computing and storing. So roughly speaking, they're very, very, very successful. I mean, it's a very obvious statement. Successful for extremely efficient exact computations. So and as such, I think I mean, there is nothing really wrong with them. So that I mean, we would need a special new design. Also, maybe you're also aware that so this technology has reached more or less its limits in terms of the performance, in terms of number of numbers of gates or transistors per unit of the chip. And as such, I mean, this further can be translated to a number of well, to the frequency on which the microprocessor works. I think. Let me see. Yeah, let me come to this slide over here. Again, I'm maybe not an expert in really low-level electronics, but on level that is sufficient to me, I think the main reason, the main problem with the current technology is that, first of all, we cannot kind of minimize the size to infinity, basically. So there are physical limitations on the size of the transistors, but also, I mean, so we are talking about electronic devices, and so the technology, and all these transistors that are placed on the wafer on the chip, they need to be supplied with a current. Again, that's kind of obvious. And all of them, so this current needs to really reach to all I mean all the elements on the chip. And then what is important is I mean the current computing so it's made. I said it already. It's made for exact computation. So it's like zeros and ones. So that's what we are computing with. And as such, it is essential actually not to make mistakes. So if you, for example, have a bit pattern indicating certain number or encoding certain number, then basically flipping a bit can change an order of this number. So bit flips is an issue. But these bit flips, so there are different reasons for these bit flips. One of these reasons is really the kind of robustness of switching between different states of transistors. And this in turn depends on the kind of voltage that you supply, which translated into current that floats on the chip. To make and again, so roughly speaking, so to make all these exact computations possible, so all current chips, they over provision with the voltage. So so they operate in this kind of reddish zone, which makes computations robust, but also which result in kind of more power you spend per this elementary operation. And there is this sweet spot, actually. I mean, you can spend less energy. So energy is an issue. So that's what I'm saying. So you can spend less energy, but then and then obviously your microprocessor will become more energy efficient. But so this, I mean, the more you save, the less exact or the less accurate it will be. And then there is this threshold where basically the supplied voltage is not enough for this precise operations, and basically the microprocessors start to produce errors. So roughly speaking, and but it's interesting that already now we can make a link that to, for example, AI functionality. In AI world, I mean, the exact value, for example, of the state in the neuron is normally not an issue. So, I mean, we are working with statistical computations. So all our results, they tolerate certain number of errors. So, and in principle, if we would end up in this area where we spend less energy, and the electronics will be kind of less reliable, but still good enough for AI purposes. So that is kind of the main motivation for these specialized computing architectures. Next thing again to mention is this bottleneck of von Neumann architecture. So the bus, so between the computing device and the microprocessor unit and the memory. So so this is another limiting factor. So, and in principle, so it is yet another place where you can one can do optimization. And as such, so there is ongoing research, and already it's not a really kind of academic research; it's applied research and real development on creating this kind of hardware, which would consume orders of magnitude less energy for computations. It will be not precise, but still would be enough for AI computations. And basically, two currently popular, so to say, approaches are in-memory computing. So chips were basically eliminating this computational bottleneck. So you can do some computations directly in the memory. And second approach is computing with spiking neurons. So and basically this type of hardware is normally by default referred to as neuromorphic, meaning that a hardware that mimics the behavior of biological neurons. But that's what I mean, first message. So two main probably branches of alternative hardware, computing hardware, that's kind of tailored to machine learning or AI functionality. And these ideas, they are not new. That's nothing that has started like in 21st century. I mean, the ideas of creating kind of low power, less precise hardware existed. I mean, it was developed in virtually in parallel with the von Neumann architectures. So analog computers existed back in the 1960s. It just happened to be that this von Neumann computers was really successful for the bulk of this algorithmic tasks, which requires fast, exact computations. That this technology won. But this computing with randomness existed for a long time ago. So again, this slide is mainly for kind of visual memories of you. So there is a technology which is called phase change memory. So it's memory unit with changing states, so you can use it for computation. So it works more or less as well as a gate, but using a different principle. So if you want to know more about this technology, so you can read this article from, again, a colleague of mine at IBM Research in Zurich, so in measure electronics, where they describe this technology in great details and show the examples of computations. But in very, very short, so they have created a unit for basically constant time search. So here we can kind of maybe link it to our discussion in the early classes on this KNN. So I mean, search is one of the bottleneck operations. So if you, I mean, the larger is your data set, the longer is the search time. And so here, what they do, so they created a chip for constant time similarity based search. So they basically encode I'm just trying to choose carefully a correct term. They use they encode features of specific particular phenomenon, so feature vectors, in say in rows of this chip. So and then basically the query, so the one that you try to find the nearest kind of the closest match is supplied, is basically tested with all these vectors simultaneously. And the vector that's kind of closest to the query will manifest itself through kind of a higher voltage at the input. But nevertheless, so so in memory computing, so if you want to know more, so this is the article to read about. But then the question is, so what kind of patterns we can, I mean, what kind of vectors we can store in such memory for this kind of constant time search. So the second variant of this specialized hardware is spiking neuromorphic hardware. So there are different kinds of it. So I'm in particular involved with Intel's development line, which is so that they have a microprocessor called Loihi, and they have a research community, so Intel neuromorphic research community, which is dedicated to programming of this this chip. So basically, what is going on here? So let me see if I have it somewhere. Do I have it? Yeah, it was here. So basically, they implement these operations of biological neurons on the chip. So in chip architecture, so both types of neural functionality. So they integrate and fire neurons, resonate and fire neurons, and again, so if you haven't been exposed to spiking neural networks, I mean, for you, probably at this very moment is enough to say that the main difference from the artificial neural networks is that our neurons, they work with spikes, of voltages, which are propagated through complex network of synapses, and so there is a kind of relationship between kind of spikes that are kind of initiated by certain input, so to say, and kind of spikes that spike patterns that represent the response to some external input, so to say. And there are different ways how this relationship between this spiking patterns happens. So one is integrate and fire, and another one is resonate and fire. So, and so the learning process is really about finding the conditions that one spiking pattern is transformed in, so to say, the target another pattern with desired properties. on a very high level, so to say. And that Laihi chip, so it's one of the possible technologies. So it implements this neural dynamics in a silicon, so to say. So here is the initial publication describing the architecture, if you're interested. Here again, so what you can do with it, so you can do different things. The primary kind of working mode with this spiking technology is really to use the advantage of dynamics. So you can think of a chip as a kind of really as a kind of an emulator of a dynamic system. So so there are many problems in like control problems and the other problems in real world that can be formulated as a dynamic system. And if you're kind of able to map your desired dynamic system into the activities on the chip, then you can compute its performance way quicker than on traditional architectures. Why is that so? Because on the traditional architectures, to analyze dynamic system, you need to compute basically differential equations. Here, you don't need to compute differential equations, so they are implemented on. This dynamics is implemented in the hardware, and in this way, so you, instead of kind of computing differential equations, you basically so if you're able to formalize your problem appropriately, so you kind of run an emulation on a chip, and then it converges to some stable states, and that happens extremely fast and at low energy. But you can also use it really as you can use this technology really as a neural network. So you can train a neural network in a way that so you can supply a pattern, and then you can have a certain so your neural network would produce certain output. It can be a classification task. So you can again, so you supply a feature vector on the input, and then you have so this neural network in the middle, and then it will produce, for example, a category to which this it would belong. So kind of one-hot encoding. Or you can what you can do again, so and it's a big deal apparently. So you can do very efficient search. So you can encode, so you can use neural network as a memory. So you encode your data set into neural connections, into synapses, and basically so you test all of them at once. So in this case, so your search time again is constant, but of course you lose on parallelization. So it's with respect to energy efficiency. But so if you want to know more, so how memory is organized on spiking neural networks, so here are two notable publications on that one. If you ask me, so I think in the future we will see some convergence of these approaches. So it will be both kind of in-memory computations. It will be hybrid spiking / digital proper for Neumann architectures, which kind of together perform very efficient computations for the different purposes. One of the challenges, again, so as I said, in this course, we are not concerned with neuromorphic hardware, is really, I mean, what I want to highlight is really the development approach. And I personally find it kind of challenging. So I don't know how you perceived it during the course. I am a computer science person in the background, so I used to work with data structures. I used to work with symbols. I used to work with algorithms and programs, and a kind of a straightforward way, like if then like programming. So this is my mindset on the right, so to say. If you would if you would try to enter this neuromorphic domain, then you should prepare to tune your mindset to something, electrical engineering stuff, and really, it's better that you understand really the dynamics, at least the basics of dynamics, and to start to approach programming. But even then, so again, this is my personal kind of reflection on it. I find that this area is very, I mean, it's not only electrical engineering inclined, but also very biologically inclined. And I find it really, really challenging to think in terms of neurons and synapses and the membranes potentials and such when you think about, for example, training of a neural network, so like an algorithm. So to me, it would be great to kind of have this transition. So I mean, I don't care so what kind of hardware I have. Presumably it does its job on doing some power efficient computations, but I want to approach its kind of interaction with it in a kind of traditional symbolic manner. And that's what's amongst others I'm working with, and again together with my partners from Intel as well. Yes. So what I will be talking about is how to really, I mean, the way to represent different concepts as patterns or as kind of vectors which are both suitable for kind of in memory computations, but also kind of compatible with this spiking spiking hardware, and yet kind of have relationships to data structures and symbols and such. So let me see. So I will be talking I will be talking about a theory which is called hyperdimensional computing. So another word is vector symbolic architectures. So let me see. Yes. Let me see. Again, and so this course is more, I mean, practically, so we focus on really machine learning stuff. But again, so it has, at least in its name, it has this artificial intelligence definition. So, and artificial intelligence, as I have mentioned before, is way bigger or way more complex problem. I just want to highlight one thing, which is, and again, I mentioned it in the introductory part. So the reasoning, really, the reasoning, knowledge representation, and such. So really the part of the intelligence that enables our complex cognitive abilities, not only learning certain representations. And again, I will not go into this topic in any detail, because it's a topic for entire topic for the course. But we have this. I mean, so we treat all objects in the around us. I mean, as collection of attributes which are organized in different relationships to, and then we make sense out of it. And this structure, it exists in the it exists in all aspects of our world. So if you look at like chemical formula, so for a given element, so there is a structure over there. So language, so there is a structure. So this structure and relationship, it exists like virtually anything. So the problem is how to really, it's a challenge. So how to include this hierarchy and structure in the learning process. So what to learn? So again, so if we talk of, I mean, if you just listen the current state of the art, like artificial intelligence is really about like deep learning, transformers, like large language models, and so all about learning based on data. But then the question is really everything learnable, or we can really can at least make some shortcuts, so we can introduce certain assumptions in the learning process. And by the way, so practically or technically, this process of introducing certain assumptions into the learning pipeline about the data or the domain that you work in is called an inductive bias. So anytime you kind of introduce certain, so you have certain assumptions, for example, that a word is defined by its neighbors. So this is your assumption. You can learn it, maybe. I mean, if you have like a huge CNN, like working for, I don't know, weeks, maybe you will, and again, so you would construct a neural network to learn these relationships, basically, maybe you can learn it. But question is whether there are other ways to kind of incorporate this bias, inductive bias, into learning processes. So let me skip this stuff over here. So, and that is here where we come to really the theory. So this distributed representations or high dimensional representations, hyperdimensional. Shall we make a break? Yeah, we make a break because we start to lose people. Yeah. And then so, but only 2 minutes. You manage? Yeah. Okay, good. Yeah, we make a break here.
I have a little question about Log 3.
Yep, sure.
Because I'm not sure I understood like what's the goal. So the goal is to see what language is the text, right? Okay, so and then my other question was using n-grams. It's n-grams of words or characters?
Characters.
Yes, okay, so I understood it. Right. Okay.
And I will comment on it. So what would be the main kind of optimization? So if you use this vectorized representation, so compare it to traditional way. So you basically you list all n-grams.
Mm-hmm.
So you have a huge list, right? So
Yeah.
all combinations, and then you collect the statistics.
Yeah.
Okay. So here you can encode n-grams iteratively. So I mean, you really can create them on the fly.
Okay.
Hmm?
What do you mean?
I mean that I mean, when you parse, so you don't need to
to create them, like for example, for n-gram, I don't need to create
exactly. So you just create them on the fly when you
Okay.
so with these codes.
Yeah.
With these representations. So that's kind of one of the optimizations.
Yeah. Okay. Okay.
But your understanding is correct. So yes, we do classify the language, and it's character-based.
And does the space is considered like a space, is it considered as one character in n-grams, or is it real characters? Like
that's a regard. Okay. Space. I think you can treat it. Well, it's the same kind of question. So whether to treat it as a character or not.
Okay.
So you can try both, but I would say you treat space as a space. So so it's a character.
Okay.
Basically.
Okay. Okay.
But you can try both.
Up to us, I guess.
Yeah, it's up to you basically. Yeah.
Because then on the data set link you sent, I think like it was mainly like German. So that's why I didn't know.
Really?
Oh, yeah, I mean, I haven't started with lab 3 myself, but I was checking through the files.
Yeah.
And I clicked on the link, and
I mean,
I don't know if I should go deeper into the website, but I have just seen that the data set is based on the German users.
No.
You can go deeper, and then you have like a huge list of different languages.
Yeah.
But then I don't know like which one we should take, which like.
No, I mean, yeah, that's a good question. So let me comment on it. So
But the direct link is only for German.
Yeah.
Like if you click
yeah, the direct, yes, but I mean, then you need to go to the main website and select other languages.
Is there like a huge data set with like all the languages included already, or do we have to download it?
I mean, this mat file that exists under module 2.
Ah, yeah.
So that's a kind of a clean, short data set with 21 languages already pre-processed, and I think without space. Yes, so you can have a look. So this mat. No. I mean, look. What I mean is this one. So let me see. So this mat file, languages data. .mat.
Yes.
So it contains a clean data set. I mean, we created it. No, you do. I mean, you can have a look how it should look at the end.
So
But you
part of the objective of the lab.
yes, to
create a clean data set.
exactly. But I mean, you can have a look how I mean this how it should look at the end.
Or maybe not how it should look, because like if you take it in another direction, you can make it work your own way, but like this could serve as inspiration.
Exactly. Yeah. Mhm. Yeah. Yeah.
Because I was not sure if I understood it right since.
But we can do like you can do like this. So I mean, it's total, and I think so. People in Zoom also can hear me. You can try both. I mean, you can try the method on this clean data set first, and then on your data set. And on your data, I'm pretty sure that first results will be, I mean, really weird because of the special characters and such. Yeah, I mean, when you will clean it, so maybe the very first time the result. Yeah.
Okay, yeah. Like if we get a 50% accuracy here, let's say
Yeah.
30% accuracy will be bad for us.
Yeah.
Maybe 40
Yeah,
or
yeah,
45 is
yeah.
like towards the direction.
Yeah.
I guess.
All right. So let me just quickly go through this stuff. So I need to again do this. My personal interest in this topic was initiated from the work of this person over here. He's a Finnish researcher or a researcher of Finnish origin, but he lived the most of his life in California, so worked at Stanford / Berkeley. And so he is now like in his 90s, but still an active researcher. I mean, that's kind of, to me, it's the reference of, elderly people who, I mean, where you want to end up eventually, basically. And he dances still. So dances, participates in our webinars and supervises PhD students. Fantastic. But so he published several works. Again, if I were you, I would be really interested really in the idea. So he approached certain machine learning or intelligent functionalities from like biological inspiration. So that that somehow in memory, so we create associations on the fly. So how would one organize such a memory? So what does it mean? And so if you read this work, sparse distributed memory, so it's one of the possible ways of doing that. But then practically, so his observation was that I mean, in the brain, so we I mean, like even simple concepts. In most of the cases, so I make it in quotes, so a large number of neurons are activated. So like it's even some simple stimuli activate very large number of neurons, like thousands or tens of thousands or hundreds of thousands. And so this quotation was about observations about special neurons that are kind of are activated on very specific concepts, like there is this terms like grandmother cell or Jennifer Aniston cell, something like that, yeah. So basically cells in the brain that's kind of tuned to be activated on some very specific stimuli. Yes, they are, but I mean, kind of in many other cases, so simple stimulus, they generate patterns, and that was the starting point, basically, to start thinking, okay, but what if we have this kind of we do all these computations on these patterns of large dimensionality? So like we will include like everything, like atomic concepts, data structures, variables by randomly generated patterns of large dimensionality, say 10,000. And he was thinking in kind of binary patterns, so basically binary words of length 10,000 in his way, so compared to say 64 bit long words in the computer. And so he suggested like an algebraic operations and mapping to so giving some meaning to these operations, like introducing semantics which are relevant in the learning context. And we will see now what does it mean. And then this gentleman you can even bump into here on the street. So he's now he's also one of the pioneers in this area. His name is Dmitry, and he worked in Ukraine, Ukrainian Academy of Sciences, all of his life. And since because of the war, so I invited him here. So he's working with us now for 1 year now. But so that was also back in kind of end of 80s. 1980s. So he worked with well, he actually also started pretty much same assumptions that, okay, we have this high dimensional representations in the brain, but also, I mean, so there is a key observation that these activations are sparse. So it's like we have this millions of neurons, but not all of them are activated. So a single concept activate only kind of short portion of it. And so he worked out computing framework based on this sparse high dimensional representations. And it's interesting again. So I mean, I find it kind of interesting that, well, now we are. I mean, it's really the top time for artificial neural networks, which actually was simply one of many other approaches. Actually, not very successful in the beginning, but thanks to backprop and such, so we have what we have. But back in 1980s, around that time, so very popular ideas was about this biological inspired computations and neurocomputers. So now, I mean, we talk about neuromorphic processors. At that time, it was really people were thinking about neurocomputers. So computers that do all brain functionality. And so one of the concepts was developed in the research institute where he worked, and which, I mean, that time it was Soviet Union, which is actually, I mean, this institute was worldwide famous for that. But again, so hyperdimensional computing, so the computational framework that I'm working with for different purposes is about, as I said, representing everything as high-dimensional vector. And then we have this algebraic operations. Why? I mean, what is the catch here? Why this high-dimensional? Of course, it's biologically inspired, but not only that. So here we come to some interesting thing. So let me see. Again, so we will not go into math. So math can be quite challenging here, but it is about considering a vector space. Okay, now we talk in mathematical terms. Vector space. So we have vectors, kind of different, arranged differently in the space. And we have all of them for a given, say, given number of dimensions, so coordinates. But then we need to introduce a measure of proximity, or call it similarity. So you can use, for example, Euclidean distance, but in vector space, we can also use this dot product or cosine similarity. We talked about it. I mean, it's one of the possible measures of proximity in machine learning of the distance between vectors. But then there is this interesting property with respect to this measure of similarity and the dimensionality. So the mathematics tells the following. So you randomly generate a pattern of certain dimensionality. So say we start with this 32-dimensional binary vectors. So all positions are zeros and ones, and then you start, and then you have 2 to the power of 32 possible combinations, right? 4 gigabytes. And then you start to measure this distance to all of them and collect statistics. So how many are kind of on certain distance, and et cetera, et cetera. And here, so you see the statistics plotted for different dimensionalities. So that's kind of interesting. So this blue stuff is for dimensionality 5, then 10, 20, 10, 1,000 and 10,000 is this orange one over here. So what does it mean here? How can you interpret it? So remember, so what we do in this kind of experiment, so we pick a vector in the of specific dimensionality at random, and then start to collect statistics. So how many vectors are on distance, on certain distance, say, cosine 0.5. So here it's written Hamming distance, but there is a kind of mapping to cosine there. So basically cosine 0.5. And cosine 0 means, sorry, I always confused, wait a second. Cosine 0 means they are totally orthogonal, so 90 degrees. So cosine 0 is 90 degrees between the vectors. Cosine 1, it's they're collinear, basically same vector. But that's what you start to see. So this for low dimensions. So you have quite many on. You have more or less uniform distribution of distances with respect to the chosen. But then the larger dimensionality you have, so this distribution of distances, it becomes to this very, very spiky. The interpretation in one sentence is the following. So on high dimensionalities, so the entire space. So and now you need to get this numerical or quantitative appreciation. So say dimensionality is 1,000 or 10,000. Number of combination is 2 to the power of 10,000. It's like it's beyond the astronomical scale. But the phenomenon that is shown here is also maybe not straightforward to appreciate immediately. It means that most of the vectors, like the entire space with respect to a chosen one, will be located on the distance 0.5, which is somewhere in between. So we tell, so if cosine 0 is strictly orthogonal, so basically all coordinates are different. 0.5 we call it quasi-orthogonal. So it means that so they're dissimilar to each other. So most of the space is located in this. So there is a statistically stable measure, say cosine of 0.5. No, I think it's Hamming distance. But it doesn't matter. What does it mean? It means that if you have large dimensionality, so you can at random generate patterns. So you just have random number generator, generate each coordinate randomly, and with 99% probability, these two vectors will be quasi-orthogonal. What does it mean? It means that you have a native capability of generate plenty of patterns which you can put in correspondence to symbols. So that is the first interesting kind of link to biological, to our intellectual capacity of generating symbols to virtually anything. So our set of symbols is not limited. We see something, we generate symbol, meaning internal representations for this something. And we don't need to reuse this symbol. So we can give whatever name to whatever. And then, so we would then make sense out of it. So here, that's why we work with this kind of high dimensional representations because of capabilities of generating symbols. And then what you can do here, you can do simple things. You can apply these vector operations, which are addition, kind of multiplication. Well, you can implement it differently. Inverse to multiplication and permutation. Permutation really kind of so you take certain coordinates and exchange with another, or a simple case you can do a circular shift. But again, so what's the catch here? The catch is the following. When you, well, that's a kind of rough visualization of what happens with respect to this similarity measure. So if you take two randomly generated patterns, say symbols, A and B, and you add them together, like coordinate-wise. So you take the result, so this pattern of the result, and then you compare. Then you compute again this distance measure of each of the components to the result. This result is no longer kind of orthogonal to them. So it will be more. It will be very similar to both of them. And then it's kind of used to. This kind of operation has a correspondence to collecting items into a set. So meaning that, so in one vector pattern, so if you create it by summing up quasi-orthogonal vectors, so it means that this result collectively represent all of the components. So in a way, you can you encode a set of variables. What you can also do, you can use multiplication, for example, but for multiplication, it works differently, but the effect is different on this distance measure. So you take two quasi-orthogonal patterns or vectors, multiply them together coordinate-wise. So here we use coordinate-wise multiplication, which is also called Hadamard multiplication. And then you take the result and compare the similarity to the components. And in this case, you got this result is quasi-orthogonal to both of the components. And this is used. This operation is used to. There is this concept in cognitive sciences of to bind concepts. So if you want to create a pattern that kind of binds together two concepts, then you use this multiplication operation. But now let me probably switch to this slide, and it will become a little bit more evident. So apparently you can, with this kind of encoding, you can think of representing different structures in a single vector pattern. And that's what you actually do in lab 3. And that's what you actually also did with random indexing, if you think about. So now you will see. So so if you look at, for example, this stuff over here. So this is the way to create n-grams. So you have, well, one of the ways. Let me see. Yeah. For example, so you have symbols corresponding to A, B, and C. So, or you have generated this randomly generated patterns and say, okay, pattern 1 is for symbol A, pattern B for symbol B, second pattern for symbol B, and in this way you generated patterns for the entire alphabet. So what you can do now, you can also generate another pattern and say, okay, this pattern will be will encode position. So we give a meaning. So so this is pattern of a position. So position, single position, it will be this vector. So if we want position number 2, so we need to well, we generate another pattern based on the previous one in a controlled manner. So this row over there is a permutation. And in this way, so you basically create a position-based encoding, so that A on the first place, B on the second place, and C on the third place. But what is important to us, so you don't keep all these atomic vectors. So what you keep here is the entire, is the result. So the pattern that basically encodes certain sequence or ordered sequence of symbols. And then you can think of encoding all other structures like graphs and trees, or I don't know, a matrix. And now probably, I don't know, maybe it's not very evident from the beginning, but the catch is that later on, so you can use these results as an input to your machine learning model. So it's this is the way how you can kind of natively introduce this kind of inductive bias about your task. So if it is n-grams, so you don't kind of create this kind of very, very sparse vector and just enumerating all the n-grams, but rather you create a kind of a fixed and smaller dimensionality here. So this you can read about in this cited article for lab 3. Yes. And that's what is going on also with random indexing in lab 2. So you remember, so the plain random indexing is about well, you create you want to create embeddings for each word based on the count of this word in different documents. And so instead of kind of listing all these documents, so you encode them by patterns of fixed dimensionality. And what is happening is that so each word, so in this way, so you create a kind of so each word vector or embedding is nothing more than just a bag of documents, so codes encoding the documents. And so that can give you a sense of what is going on. So in the same way, let me see. You create a context. So that's the kind of next modification of random indexing. So you create a vocabulary of all possible words. So you have a dictionary of all possible words. You assign. So first, you don't give any meaning to it. So and it means that you assign random patterns. So just each word is just certain pattern, and then you start to create this context. So this structure. So to encode word B, so you start to collect so the ordered sequence. Some words before, some words after. So you don't learn, so you just, I mean, this is your assumption that the word is defined in this way. In word embedding, so you do it by choosing the structure of the network. So that, I mean, how many words you kind of supply to the input to learn the output representation. So here you do it with computations. So what you can do with it, and this is quite interesting. So this is one of the results that actually was better than state of the art with neural networks. You can take the discrete, in times in analyzing or classification of time series. So you have a time series, and then you can, well, if using different methods, you can extract. You can extract descriptors, so basically on portions of this data, and then you can do it on many different time scales, but at the end, so using this kind of operations, you can aggregate them into a single representation, which then you can supply as an input to your machine learning algorithm to for the final to learn the final classification. So this n-gram, so that's what you will be working with, lab 3. So so you can again, so you can use this representation. So that's what you use, by the way. So when you encode this n-gram stuff per sentence, then so according to the lab description, so you sum them up. So into a vector corresponding to a specific language. So, but I mean, this is just one way of creating the final discriminative model, so the classification model. So what you can also do, you can, for example, input it to a self-organizing map. So for kind of unsupervised learning, or to perceptron, or doesn't matter. Yeah. Let me see. So using this kind of algebra, what you can also do, you can encode. You can encode continuous spaces, or practically you can use for encoding certain coordinate system. What is it useful for? Again, maybe this is a good example. Again, state of the art from 2021, and it is about visual place recognition task in robotics. So which is formulated as following. So a robot so records images, so it has a camera, and so it let traverse certain area and do video recording, and then so this video recording is stored in a database, and then you place a robot somewhere, and it should recognize where it is, basically. So looking at the current scene, match where to which of the frame it corresponds. Nearest neighbor search again. But what is happening here is that you can analyze. So again, one of the practical challenges with the machine learning is that you can tackle specific problem with different methods. So specifically here, so with image analysis, so you can have different ways to create so-called image descriptors. So meaning that, so you can, for example, so you can train a neural network like whatever convolutional neural net. So this AlexNet or so something, and then you can so you supply an input, an image as an input. So downstream maybe it's a classification task, but what you can do, you can take the last convolutional layer, so you flatten it, and then you use it as a representation for this image. So embedding. So that's embedding basically. But this is one of the ways to create an embedding. So you can have many of these methods. So some of them can be even kind of handcrafted. So you take like a point and then kind of a neighborhood around this point, so in a certain pattern, and then so you characterize an image in this way. And interesting thing is that each so one descriptor works better on one data, another descriptor works better on the other data. The problem is that it's practically challenging to, for example, keep multiple copies of these descriptors. So if you have your data set, I don't know, some thousands entries, So the more descriptors you use, so it basically adds to this memory and also to the search time. So what they did here, so they took these different descriptors, and again, so what descriptor is the kind of human understandable term, but in a way, so each descriptor is nothing more than just a vector with certain similarity property between other vectors encoding other images. And so took this vectors from different descriptors and combined them into a single representation. So just mechanically kind of aggregated all descriptors in a single representation. And in this way, so and then they use this kind of aggregated descriptor to train, I don't know, last leg classifier, or whatever it was. And in this way, so it became kind of it took best of all possible descriptors in this model. So maybe this would be the last message. So this technique that I'm presenting and that you work with in Lab 3 is really a powerful way of treating your data and interfacing to machine learning models. So basically, kind of it creates lots of possibilities for creating this novel inductive biases that they enhance the quality of the models. Right. Yeah. So try it out again. Well, you will try it out in Lab 3, but if you're interested in learning more, so there are sources in this resources mentioned in this presentation. I will make it available after the class. Any questions? No. Well, if they are, if there will be some, so you know how to find. Good. Then we'll see you next Monday.
Thank you. Thank you so much.
Yep. Алло. Привет, что я на лекции был? Ну, подожди, следующий. Ну, хорошо, я на лекции просто. Ну, окей. Пока.
What are you doing? 20 seconds.